Good morning students. Today we are going to discuss few topics from chapter 2, that is units and measurement. Already we have started this chapter and we have completed many topics. Today we are going to discuss this topic and we will try to wind up this chapter. Now the topic which we are going to discuss is your error in exponent. Already we have discussed combination of error, only this topic is left out, that's why we are trying to explain this topic today. So the topic is your error in exponent. Now here we have given an expression z equal to a to the power n. Suppose you are performing an experiment and you have to define z, and the expression which is given to you is like this: z equal to a to the power n. Now if you have to define z, definitely you have to define capital A, is not it? And n we are assuming here is a constant numerical value like a square, a cube. So n may be 2, 3, 4, 5, even it is in fraction also. Now in measuring capital A, there may be the possibility that you are earning some error. The error may be from instrument point of view or from observation point of view. So already we have discussed the error part. So if you are absent, please check it out, the videos which you have given in Google Classroom. Now suppose in measuring capital A, you have earned some error, and let that error be delta A. Delta A basically a very small value of capital A, because we are assuming that we are performing the experiment very sincerely, and instead of that we are earning, and instead of that we have earned some error. So if delta A be the error in the measurement of capital A, then for the error delta Z in Z, because once we substitute the value for A after measuring, if it carries some error, then definitely in Z also there may be some error. So if delta Z be the error in Z, then Z plus minus delta Z, A plus minus delta A bracket to the power n. And here we are assuming plus minus sign because error may be more or less than that of the actual value. So that's why we are considering plus minus sign. Already we have defined, please check out. Now simple mathematics, take out capital A common, so 1 plus minus delta A by A, second bracket to the power n. So a to the power n, 1 plus minus delta A by A to the power n. So a to the power n is your z 1 plus minus delta A by A to the power n. So z plus minus delta Z by Z, 1 plus minus delta A by A to the power n. So here we are using binomial expansion, considering that delta A by A is very small, less than 1, very small, and even it is less than 1, because delta A is very less compared to capital A, because we are performing the experiment very sincerely. That's why this fraction is very less than 1. So if it is very less than 1, then this infinite series become finite, and you do have only two terms, 1 plus minus small n delta A by A. Binomial expansion, you check it out, or already we have defined in our previous class. So 1 goes off, plus minus delta Z by Z plus minus small n delta A by A. So ultimately we will get delta Z by Z equal to small n delta A by A. So you have seen that relative error in Z, delta Z by Z is basically relative error, is nothing but the exponent times that of the relative error of the physical quantity which we are measuring in defining Z. So this part is very important because in numericals we are going to use this expression. Now this is all about your error part, combination of error part. So please check out the previous class if you are absent. Now what we'll do, we'll try to implement this formula in one numerical, and the numerical is like this. A physical quantity P is related to 4 observables, small a, small b, small c, and small d as follows. So the expression is like this: a cube b square d root c, and the percentage error in the measurement of a, b, c, d is given as your 1%, 3%, 4%, and 2% respectively. What is the percentage error in the quantity P? So already we have defined that relative error is nothing but the exponent times of the relative error of the physical quantity which we are measuring to define that physical quantity. So here Z is the physical quantity, and here P is the physical quantity, and obviously A, B, C, D is also physical quantity. So P equal to a cube b square d root c. So delta P by P is nothing but 3 delta A by A, 2 delta B by B, because when you define P, you will measure A, B, C, D. So in each case you are earning some error. So if I ask you to define the relative error in P, then definitely you are trying to add up that error. Okay, whether it is denominator, that does not matter, but you have to add up. So delta P by P, 3 delta A by A plus 2 delta B by B plus delta D by D, half delta C by C. So exponent means root over is your half. So half delta C by C. So as per here A, B, C, A percent to define percentage error, then definitely we have to multiply 100 with the percentage. This is very simple. Probably you have done in lower class, and also we have discussed in our previous classes. So 3 delta A by A is your 1%, 2 delta B by B, that is your 3%, delta D by D is your 2%, and half delta C by C is your 4%. So 3% plus 6% plus 2% again plus 2%. So if you sum up 6, 10, 13. So percentage error is your 13%. So in this way you have to implement the formula to define the numericals. Please check out. It's very simple. Now next topic we are going to discuss is your significant figures. Already you have gone through this topic in chemistry class. So we are trying to brief it out. Now it's very simple. So let me read out what we have written. The significant figures are normally those digits in a measured quantity which are known with certainty, or reliably, plus one more digit that is uncertain. So significant figure is nothing but a combination of certain and uncertain digits. Now which are uncertain, that part let me take one example. So suppose time period is your 1.72 second. So 1 plus 0.7 plus 0.002. So the least value is your uncertain. So 1 and 0.7 is your certain or reliable, and 0.02 is your uncertain. In case of length, 273.7 centimeter, that is your 200 plus 70 plus 3 plus 0.7. So least value is your uncertain. So these are the certain, these are the uncertain, or these are the reliable, these are non-reliable. So larger is the number of significant figures in a measurement, higher is the accuracy of measurement, and vice versa. So if significant figures are more, then more means number. So definitely the accuracy is more, and vice versa. Now a few rules are there. I think already you have done in chemistry class, or you go through the textbook. It's very simple. Few rules we have written. All non-zero digits are significant, number 1. Number 2, all zeros occurring between two non-zero digits are significant. Okay, the trailing zeros in a number without a decimal point are not significant. So like this 4200, if you write, then the significant figure you do have 2, not 4. 4200, because that 0 you have to you are not supposed to consider as a significant. The trailing zeros in a number with decimal points are significant. Okay, this part is very simple. Please check out. Now rounding off part, this thing you already know in lower class. If a digit to be dropped is less than 5, then the preceding digit is left unchanged. You are not supposed to add 1. If a digit to be dropped is greater than 5, then preceding digit is increased by 1. So you have to add 1. This is very simple. If a digit to be dropped is 5 followed by digit other than 0, then the preceding digit is raised by 1. It's very simple. So more points are there in your textbooks. Please go through. I think you have done in chemistry class. So it's very easy to understand. So this is all about your chapter 2 because we have spent quite a number of classes for this chapter 2. Please go through this topic and find out your doubt, and next class we are going to start a new chapter. If you have any query, please ask. You are free to ask. Thank you.